Hi everyone, welcome to the senseFly Academy session of today. I have with me Nathan Stein from the Ag Application Engineer team in the US, as well as Dan Murphy and Matt Delano. Topic of today's session is filling the gap between UAVs and agronomy. This time we really try to go through some basics of remote sensing. We'll be talking about electromagnetic spectrum, spectral signatures, sensors to detect characteristics of spectral signatures and factors influencing that data. Furthermore, we'll then look into different types of indices, how and why and when we can apply and calculate them. So, remote sensing. Remote sensing is the science of collecting data about an object without making physical contact. This is normally done through satellite or aircraft-based sensors. It used to be only satellites and airplanes, and these days we're also doing it with drones. But what are we actually detecting? We detect signals in form of electromagnetic radiation. So it can be radio waves, microwaves, infrared, visible light, ultraviolet, X, and gamma radiation. These might all somehow sound familiar to you, but you may not know where to line them up in the electromagnetic spectrum or what this all has to do with remote sensing. So let's look into that. All those types are waves of the electromagnetic field that propagate through space at different frequencies. These frequencies and wavelengths can be used to characterize each type of wavelengths, which can then be sorted out or laid out on the electromagnetic spectrum, as we have it here. We see on the left-hand side we have frequencies that are high, increased, and on the right-hand side we have longer wavelengths, lower frequency wavelengths. Left-hand side, gamma rays, X-rays, which are apparently not super healthy for us, as well as the UV, which is not our skin doesn't like so much. And then we're already entering the visible spectrum. It's called visible spectrum because that's what the human eye can see. That's genetically defined. We will never be able to see any other radiation in any of the other areas of the electromagnetic spectrum. The visible spectrum ranges from 400 nanometers to 700 nanometers, where at the very edge of the red, we have the red edge, which we'll talk about later as well, since it is important for the type of analysis that we want to do. After the red edge, we go right into the near-infrared section, and you see the infrared is actually quite a large part of the electromagnetic spectrum. So if we're talking about infrared, it's important to specify which kind of infrared we're talking. First of all, we have the near-infrared, and just following after the thermal infrared. They are quite different, though, in their electromagnetic wavelengths. We have the near-infrared from 780 nanometers to 3 micrometers, so they become quite long compared to the visible one. And the thermal become even longer. They only ever start at 7.5 micrometers and go up to 13.5. So all these radiation types or wavelengths are either reflected or emitted and then can also be absorbed. Each object, therefore, on Earth has its own way of reflecting or emitting these electromagnetic waves. And we can therefore chart that reflection of an object for each type of wavelength, which gives us a specific curve for that specific object. It's called the spectral signature. Here we have such a chart. At the bottom we have again the electromagnetic spectrum, where where we start though with the visible light, so 400 nanometers going through the 700, where the visible finishes and going into the near infrared. On the left-hand side here we have the percentage of reflection, so the intensity of reflection. Looking at the water curve here, for example, so the spectral signature of clear water, we see that it has a high reflectance close to 400 nanometers, so in the blue area, and then descending until it's hardly reflecting anymore in the near infrared section. This is why we perceive water as blue. Like in the visible, it's clearly the blue that the water reflects the most, and therefore we see water as blue. If an object reflects all visible wavelengths in about the same amount and a high intensity, like up here, we perceive those objects as white, like snow, ice, and clouds. But what interests us is actually the spectral signature of plants. You see here we have again spectral electromagnetic spectrum and the reflectance intensity on the left-hand side, and these are the spectral signatures of a healthy plant in green and a stressed plant in orange. Brown is soil, just to have a reference. You see there is a clear difference between the soil signature and the plant signatures. Now, for the plant, it's quite obvious that in the area of the visible wavelength of green, we have a peak. Then towards in the red, we have a dip. And then we have the red edge where we clearly see the climb back up. And then very high values of reflectance in the near infrared, where there's a clear difference whether you have an unhealthy plant or a healthy plant. Now, why do we have this type of curve? There is a big interaction between chlorophyll and solar radiation. A healthy plant absorbs strongly, or because it contains a lot of chlorophyll, it absorbs red and blue, reflecting green and near infrared. Near infrared is reflected more strongly than the green, as we saw here in the signatures. But the near infrared is not within the visible spectrum, so we don't see that near infrared reflection. The green, on the other hand, we see. So our eyes perceive a healthy plant as green. On the other hand, if an unhealthy plant who doesn't contain much chlorophyll and therefore doesn't make such a big difference in reflecting blue, red, and green, it will mainly reflect in all of them in about the same intensity. We get a mix out of red, blue, and green, and therefore we see the plant as brown or yellow, which is clearly an unhealthy plant. So we do see the difference, but if that difference is not strong inside the plant, we don't have a way of detecting if the plant is about to become stressed. Therefore, it's very useful to have the information of the near infrared. And that's why we're creating sensors that detect certain characteristics of these spectral signatures. With the green band of for example here, the Sequoia sensor, we detect the first peak here of the spectral signature of a plant. With the sensor for the red reflection, we detect this dip here, and with the sensor for the red edge, the climb up and here around just the edge of the visible spectrum, and then with the near infrared sensor at around 800 nanometers, we detect nicely these big reflectance values of the plant, which to our eyes are not visible at all. So the output of the sensor here, or of these 4 bands, wavelengths, radiations, are mapped in a picture. Actually, in 1 band per picture. And therefore, we have here on the left, we have the near-infrared data displayed in 1 reflectance map, and the red data in another reflectance map. Now, why would exactly those 2 be interesting to us? When looking at the spectral signatures of plants, we have the dip here in the red, means a healthy plant is absorbing a lot the red, and we have a big reflection in the near-infrared. The difference here between the red and the near-infrared is quite big. For an unhealthy plant, though, the difference is quite small. So comparing those 2 differences will give us information about the plant. Respectively, will tell us if the plant is stressed or in good condition. What we need to do is to just visualize this information, is just to do a calculation between the 2 images, where we just take the red band and subtract it from the near-infrared. That's all we're doing to calculate an NDVI, a normalized difference vegetation index. The output will be the so-called index map, where we nicely see in color, so visible to our human eyes, the state or the condition of the plants. Now, this sounds all nice and easy, but we have to be careful. There are factors that influence our data. First of all, we have the spatial resolution, where when we fly with an EBSQ, by default, we're collecting data at 11 centimeters per pixel. We can change this to higher or lower resolutions, giving us more or less detail. Of course, this depends again on the size of the plant, or the size of the trees, or whatever we want to look at, so that we get interesting information. There can also be too much detail, and there can be too little detail. The resolution also influences our flight altitude, where, of course, there we are restricted to flight regulations, or even restricted in terms of the actual platform. With an EBSQ, we don't fly at 500 meters above ground. We could, but it's not practical to do. Then we have the spectral resolution, which also influences our data. With the Sequoia camera, we have to be aware that we're collecting 4 bands. This is discontinuous data. From this data, we could not create a spectral signature of an object. It's not enough information. There are always gaps in between. If we're looking at hyperspectral data, we really have 1 band per 100 nanometers, and we get a huge amount of information about an object, and we can even create a sort of a spectral signature or compare the whole signature to data that has been collected previously. Then we also have effects of the sensor, where, for example, one could think, well, I can maybe add my blue band from the RGB sensor of the Sequoia camera to my 4 bands here that I collect with the differentiated sensors. Well, if you look at the blue band here, we also have some green in there and some red. So this data is completely mixed. You're not going to get clean blue data out of the RGB sensor. This is why we're going for separate sensors in order to collect the green, near-infrared, red edge, in order to really have clean data and be able to do clean calculations and comparisons. Then we also have radiometric corrections that need to be applied. These are applied to have to do a conversion to absolute radiance values, depending on the time of the day, or even if it's on a different day, the atmospheric conditions, the sun angles, everything has changed. If we now want to compare data from one day to another day, we need to sort of normalize or make the data uniform. What we have, the tools that we have to do this is the sunshine sensor, which basically corrects one image by the other. So this is a local correction per image. Plus then we have the multi-spec target, which we use to apply a global correction to the whole data set. And with this, we go now from this general course about remote sensing basics over to Nathan, who is going to talk about different applications of different types of indices.
Hi, my name is Nathan Stein. I'm the Ag Applications Engineer for senseFly, and I'm glad to be here with you to talk about indices and what they can do in agriculture, especially how they're tied specifically to agronomy. And I'm going to get into a little bit of the detail. I don't have enough time to go through all the indexes and what they are, so I'm going to choose a few of them, and I'm going to show a few applications as to what they could be used for. Now, Andrea's done a good job. She showed you kind of a little bit of background on the electromagnetic spectrum, about how light interacts with plants and what that tells us. She's also explained how our cameras capture that light and why that information is really critical for us. So that helps set the foundation as to how to do these indexes and how to calculate them and put them to use. The first one I'm going to talk about is the NDVI. It's very basic and simple, kind of bread and butter index that a lot of people use in the industry today, and for quite a few reasons, mostly because the information is it's very easy to understand and it's very simple to calculate. It's based off of an older equation called the simple ratio, and it has a high correlation to leaf area index. I find it very helpful in a situation as the picture that's shown. You can see there's water and no corn plants. You can see some fairly dense area of corn plants growing, and you can see very small corn plants up here where I have quite a bit of emergence issues actually happening, and this is early season corn. And some tips for using this, I would say, is that you need to consider the crop stages. Since it's related to leaf area index, you're going to see the numbers are very lower when there's not very many leaves out there, so in the earlier stages of a crop, and it's much higher in the later stages of crop. And each time you take one of those pictures or make a data set, you can learn a little bit of something about these plants based on perhaps the stress periods of the crop, or how they develop, or how they work. Corn isn't the only thing that's out there. It's just a data set that I have a lot of, so I use it as an example. Of course, we can use this in vegetables, in trees and other things, and in orchards. There's many other crops that uses sugarcane as well, so it's not really confined to just one crop. It's all plants kind of behave similarly, but you do need to know a little bit about the plants. Soil is another thing to consider in this index, and it's typically in the ranges of 0 to 0.3. You'll notice, especially if you're trying to take that information out of your pictures when you're filtering it. That's kind of a helpful range to remember. Another index that's important to know is the soil vegetation index, or the optimized soil vegetation index, OSAVI as it's known. Is got a factor in it that kind of helps reduce that soil effect in the background of the pictures, and can help kind of enhance the vegetation a little bit, so that you get a better look at that, especially when the crops are smaller like this, and not when they're big. You wouldn't use that index at all. Applications, there's a lot of them, But just very basically is you can evaluate plant stands, make replant decisions. You can look at the canopy development, understand which parts of the area are probably going to yield better because they got established sooner. They have a stronger plant growth. They have more leaves, and so they can digest more sun. They can grow better. So typically those things correlate very highly. I would caution though that the NDVI is not a silver bullet and it is not the only index out there. So I would encourage more investigation in these other indices, especially with a camera like with a multispectral camera that can calculate quite a few of these different indexes. A lot of people ask us about the red edge band and what can they do with it. Well, the red edge band, if you remember from what Andrea presented, is very dynamic. It's in an interesting region of the spectrum because it actually is the part between where red absorbs all that light because of good chlorophyll and it reflects in the near infrared. And so you go from very strong absorption to very strong reflectance. And so little changes make big differences in the red edge portion of the spectrum. And many studies you can reference and research link red edge to chlorophyll. Chlorophyll is very important for plant development, and we talk a lot about it. I'm not going to get into all the biology on these things, but anybody that's in agronomy knows we want healthy chlorophyll and healthy plants. Nitrogen is an essential component and has a strong influence on chlorophyll production. And so typically if you see low chlorophyll or problems in chlorophyll, you're going to see, or you can assume that nitrogen is somewhat the culprit. That's not always the case, but it's quite often the case. Couple indices to give you. There's the NDRE, or it's also referred to as the red edge NDVI. It's similar in nature to the NDVI as you see, except it uses the red edge instead of the red. And there's another chlorophyll ratio that's below here. That's a red edge ratio, and it's also very sensitive to chlorophyll and has very good research behind it, backing and documenting up that link. In the right picture here, you can see that ratio actually calculated out and what it looks like. I actually have a pass in this picture of fertilizer that was missed with the anhydrous rig, and you can see that we did not apply the full rate of anhydrous on accident, but it's a good demonstration that shows how well it detects the difference in that. And I have other ground pictures of this showing how yellow the corn was. This was just a missed application. It wasn't covering very many acres, so it wasn't something worth fixing. But in the application world, if you had this issue, or if you have areas of really strong low production or low values in this index, you're going to see, you would be able to use that to create maybe a nitrogen application or prescription. And you could evaluate the chlorophyll and maybe take some tissue samples or figure out and confirm those issues and actually do that. So a lot of applications around that, mostly around fertilizer, but the red edge band is very, very important for that reason. And another thing I would add, that monitoring senescence, or at least when the plants are dying, you can actually, this index, especially like the NDRE, is very, very sensitive to that period and watching the plants die and shut down. It shifts very quickly. At least in everything that I've ever seen or done, it's been the case. And so you can use this to go out and maybe see where your crops are actually dying or shutting down, and gauge the drying process of the crop. We also get a lot of questions about thermal data, and we have a very good thermal camera. It does a great job. There's some complex things about thermal data that I think people need to understand in order to get the most out of using their thermal camera. Thermal data is related to transpiration in a plant, how it basically breathes and digests. It's important to consider that when a plant is starved for water, it does actually get hotter, and that's proven in a lot of studies. You can find a lot of documentation on that. I'm not going to go into a lot of the physiology of the plant and all those things, but it's important to know those things at least on the surface. Now, thermal data is complex in the sense that you need to take the picture or gather that data at the right time. I would suggest taking it at the hottest part of the day typically around noon to 2 o'clock in the afternoon. Early morning is not the best time of day to gather that data because, you know, the canopy is at rest. It's past night, it's been cool. It takes a longer time to warm up that canopy and get the heat built up in it. The other thing is it's sensitive to leaf area. So this leaf area index that we just talked about with the NDVI could be helpful in understanding this issue. But generally speaking, when you see an area where there's less leaves, the sun warms the soil up behind it, and you see a lot of that heat build up in the canopy in that area. And it may not be telling you the entire truth. It might just mean that there's just less plants there. And cloudy or windy days. Well, on a cloudy day, there isn't much of a divergence in temperature. There isn't a lot of heating. It's not very hot typically, so it may not give you as much results. And in windy, really windy conditions, obviously, the wind is going to be pushing and changing the temperature through basically moving that heat off the soil or off the plants very quickly. Some of these indexes that's shown here, the crop water stress index, are pretty well accepted in the community, or at least in the scientific community. They aren't exactly perfectly easy to calculate. They actually, you know, this one I used a weather station and other equipment to get the data that I needed to calculate this crop water stress index. And on the right you can see this image here where you see a fully irrigated parcel where the temperature was nice and low, and you can see that it had a low crop water stress index. The middle had the highest stress, and you can see the red. And in the bottom you can see a 40% stress, water stress. So this just goes to show well irrigated has a low crop water stress index, and areas that are under more stress have a higher crop water stress index. Applications are pretty obvious. Irrigation management is huge in agriculture. Flood irrigation, sub-irrigation, and center pivots are prevalent throughout the Midwest and across the western parts of the United States and the world even. Water is a very sought after commodity, so there's a lot of applications with thermal. Soil moisture is also something that's very interesting to people, especially in my region. Typically areas of high water moisture are typically cooler, and we have problems with seed development and other things. So soil moisture is interesting in our area. And moisture probe placement is probably the top one thing application that people tell me using thermal data. They find the areas in the fields where it's drier or where it's average or where it's, you know, where it's hot, where it's wetter and cooler, so that they can gauge these zones in the field and use the moisture probe to determine whether to irrigate. I think they're all great applications. I'm sure there's many more out there, but that's just a few of the major ones. And another application that many people probably don't know is the multispectral data can actually be used to create false color RGB images, or just regular visual images. The image on the left was actually created from a multispectral data set that I took this spring and very easily calculated in QGIS, just using some very simple math to create this image. And I didn't have to process any more data. I didn't have to take more data like RGB images. I just used the multispectral data that I had to create an image that's actually quite useful. And these applications are very simple, typically scouting or simple viewing. People just want to see their data. They want to have it for a background for image overlays when they do other analysis. So it's useful in many other ways. A lot of people like to see this data, but I would say that it's very simply derived and pulled from the multispectral data. And we do actually have a guide on our knowledge base to do this. So I would check that out if you're interested. I just want to end with some tips here. Good data equals good analysis. You know, Andrea did a good job explaining the data and where it comes from and ways that we can get it. But you can also mess this up through taking pictures at the wrong time of day, taking pictures with heavy shadows, or, you know, that may bias the results. So it's good to know that even you know, it's good to have good operators. It's good to have good documentation when you're in the field, and it's also important to make sure you get a good calibration picture of your tile and do it appropriately so that you end up with good analysis. Understanding which index is appropriate to use is very important as well, and when the timing is to use it. So this kind of comes down to agronomy. Agronomy is important to know, these development stages, the stress periods of these plants, and practical steps, and even the equipment required to grow the crop, and when pests or diseases or any sort of pressure comes in on plants, and that's when to take those pictures. And if you don't know agronomy, make a good friend with an agronomist. Agronomist will help you with these problems, and they can help get those issues solved and tell you when the best time to take those photos are. They've been doing it for a lifetime probably, and so they know those plants very well. And another tip would be know the history, irrigation scheduling, the weather. Did it rain? Did it not rain? Influences thermal data, influences multispectral data because the soil's wet in the background. Knowing the soil types and the fertility that were in the field or the varieties that are in the crop, because each variety reflects light differently. They're a different color. They might have a different leaf structure that reflects light a little differently. So we need to analyze those a little bit in kind of different buckets. And treatment differences across the crop could also impact the way that the crop responds or displays itself in the way that light's reflected. So those are good things to know, how the farmer actually uses practices farming, like what types of tillage they use, whether it be no-till or strip-till or whatnot. All those things are important to know, to document, and to bring to the person that's doing the analysis. And finally, if the plants are too small, the data may not be so good, because if you can't actually get a pixel value or several pixel values that represent that sample of a plant, you may not get that much information that's worth analyzing. If 95% of your data set is soil, chances are you're analyzing soil and not the plants. So keep those things in mind when you're doing your analysis. I think I presented a lot of different types of applications that are available. There's many, many more, and I'm sure there's many, many questions. Feel free to reach out to us anytime with these questions, to email our teams. We're here to help you in any way that we can. I do thank you for your time. I thank Andrea, and I hope you guys enjoyed the presentation today.
And with this, I'd like to thank you for joining today's senseFly Academy session, and see you next time.